differential topology at all, differential geometry at all. Okay, it is something which is actually starting point of algebraic topology, you may say, but it has its origin in complex analysis of one variable, like many other ideas which have origin in complex analysis of one variable. The fundamental thing that I am going to use is a simple map, namely the exponential function restricted to R, but the complex exponential function, not the e raised to x of from R to R. Okay, so this is from R to S1. So this R is the not the real line, but the imaginary axis. Look at the exponential function defined on the complex plane to itself. Okay, e raised to z, you can write. Okay, e going to e raised to z. Restrict it to the imaginary axis. But imaginary axis can be identified with R. So that is why you get a function from R. But now the domain will become just the unit circle. So what is this function? I am writing it as ET for simple notation. It is e raised to 2 pi it, which sometimes I may write it as exponential of 2 pi it. Okay, which is cos 2 pi t plus I sin 2 pi t. So various ways of writing down this one. Okay, so it is the restriction or modification of cos z plus I sin z, but z is now just 2 pi it. Okay, where t is a real number. So think of this as a function from R to S1. The right hand side is a unit complex vector, right? So schematically, so here you have the circle here. Here you have the real line, and this is the exponential map. 0 will go to this dot here, which is 1 cross 0, the unit vector 1 in the complex number. Okay. So I have taken a half circle here, from here to here. What is its inverse image under the exponential function? It will be all these half intervals. Okay. Minus 1/4 to plus 1/4, minus 1/4 plus 1/4, shifted by integral units. Okay, this is from here to here, 1/4 to 3/4. So this is 1 plus 1/4 to 1 plus 3/4 and so on. And the inverse function is a log function, the branch of log function. From here to here, if you take the exponential function, it is a 1-1 mapping, it has an inverse. Okay, it has an inverse here also, but they differ by just a additive constant, integral additive constant. So all these are branches here. The exponential function is defined on the whole of it. The branch will be defined only after you delete one single point, no matter which point. One single point, if you delete, you have the definition of the log depending upon your choice. So as soon as you delete one point, the inverse image would have deleted all the points, one single point, and then they're shifted by integers. Okay, n plus that point, where n is an integer. All of them will be missing from the inverse image here from R. Okay, the rest of them is intervals of open intervals of unit length. All of them will be mapped to this entire circle minus the point that you have deleted. Okay, this is the picture of the exponential function, and I'm going to use this one only. After that, no complex analysis, nothing. You have to know this topological property of the exponential function. Okay. So this is what I have summarized here. Given any point T0 inside I, consider the open arc. I have used some notation also, which is UT0 obtained by taking the circle, throwing away minus of ET0 contained inside S1. We then have a well-defined inverse ln, which you can call it as logarithm of T0 from this interval itself, T0 minus half to T0 plus half to UT, this UT0, okay. So T0 here, T0 here, there is some typos here. So what is this ln? Ln is the inverse of the exponential function. Okay. Ln is smooth also, you know, you can differentiate. It's actually analytic. It's given by a power series and so on, convergent power series. The important point to note is that these branches of the logarithmic functions are well defined and smooth. As soon as their value at one single point is fixed, they are well defined in the entire interval, this open interval, okay, and they are defined from UT to open interval here. Okay, E is defined on the whole of R, but UT to this one, the LL, the logs are defined only on deleted circle. Point has to be deleted. Okay, here ln T0 of ET0 is T0. Okay, one value you have to pick up out of all the infinitely many values. So the infinitely many values will give you infinitely many branches of the logarithm function. Okay, so now I state auxiliary result here, which is actually the uniqueness part. I will be keeping on referring to this as the uniqueness part of the theorem. Let X be any connected space. G1 and G2 from X to R be any map such that when you compose it with E, they are equal. EG1 equal to EG2. If G1 of X0 is equal to G2 of X0 for some X0, that means they agree at one single point of the whole space X, then they are equal everywhere. G1 is equal to G2 on the whole of X. Okay. So this G1 and G2 have the property that when you compose with E, they are equal. Okay, you can think of this one as some function f, one single function f, and G1 and G2 as their lifts under E. The two different lifts, if they agree at one single point, then they are agreeing everywhere. This is the condition. This is the statement of this theorem. Okay, this is not at all difficult. Let us have a proof of this one, because this uniqueness part is going to play later on a very, very important role in the construction of the function itself, the existence part. Okay, so how do I do this one? This is a standard method in topology, used everywhere several times in topology, and people who use topology, okay, so connectivity is used to obtain certain local properties. Okay, you start with some local property and then show that it is actually global. It's valid on the whole of it. Here we have a point property. At one point something is true, then we are saying that it is true in the whole of space. Okay, that is the kind of thing that's happening. Okay, so this proof itself is a very, very important point from the point of view of topologists. Okay, people who are not interested in topology I can't help it. Anyway, they are not here anyway. So let us see how the proof goes through. Take A to be a set of all points wherein the two functions agree. We have been given that x naught is inside A. So A is non-empty. Okay. Since the functions are taking values inside R is a Hausdorff space, set of points wherein two functions agree, it is automatically closed. Okay. So this is a very important property of real valued functions. If two real valued continuous functions agree at all, whatever points they agree, that set of points must be a closed subset already. Okay. So all that we want to show is that this set A is open also. Once we show that it's open, it happens that open, closed, and non-empty, but the whole space is connected, therefore it must be the whole space. So this is the property of connected space by the very definition, that there are no proper open as well as closed subsets. Proper by which we mean that it's non-empty as well as the whole space. These two things should be avoided. Okay, it will be a whole space. Okay. So I want to prove that A is open because closedness follows by the Hausdorffness of R. Okay, how do we show that A is open? Take any point, okay, at which G1 of x naught is equal to G2 of x naught. Choose some epsilon positive, okay, preferably less than half. Then by continuity of G1 and G2, apply separately each time. There exists open subset U such that x is inside U, okay, contained inside x. Gi of U is contained inside T naught minus epsilon, T naught plus epsilon. Okay. So I have started with any point x naught. There used to be some big confusion. X naught belongs to A, already is given. So this is arbitrary point x. So you can take that x belongs to this one, and a neighborhood of G, neighborhood of that point is going inside this neighborhood. Apply both G1 and G2. Why? Because G of x naught is inside here. Okay, that's being T naught. Okay, and this is an open subset. So by continuity, G1 of U goes there, G2 of U also goes there because I have taken okay. So exponential function is injective on this open interval. It has an inverse, right? In a small interval, because epsilon I have chosen less than epsilon by 2, is half 1 by 2. So here it is injective mapping. So EG1 equal to EG2 implies G1 is equal to G2. So for all points of U, G1 will be equal to G2. That means the whole of U is contained inside A. Given any point, we have found a neighborhood contained inside A. That means A is open. Okay. So this is elementary points of topology that I am using here. All right. So some more topology like this will be used. Connectivity, continuity, Hausdorffness, and these are the only things, not very deep. Okay. The next theorem, this is the crux of the whole thing here. Take a function from x cross an interval, a closed interval, preferably 0 to 1, not necessarily. Any closed interval will do. Okay. Take a function from x cross interval into S1. Such a thing is called a homotopy. Whenever you have x cross some interval to a continuous function, interval into something, it's called a homotopy. Take such a function. Suppose you have a map G from X to R such that E of Gx, when you come back under E to S1, it is H of XA. That is the starting point here, A. Okay. So there is a whole lot of functions here. For each T, you have a map from X to S1. So that's why it's called homotopy. So I'm taking the starting point H of XA here. So that is one function. This function is lifted by G. So E of G is H of XA. Okay, G is a continuous function. Okay, the statement says that then there is a unique map G from X cross AB to R such that E composite G equal to H for all of them. E composite equal to H means for all X comma T. Moreover, this capital G is nothing but G of X equal to G of X that we have taken here, G, this starting point. The starting point for each of X comma A, X comma X is arbitrary, X comma A has been given as G of X. Okay, that function gets extended to the whole of X cross AB, and E of that function is the given function H. Okay. Further, suppose X is a subset of Rn, then I can talk about smoothness of this function. Suppose H is given to be smooth, then automatically this G will be smooth. Okay. So smoothness comes only when you take some manifolds here which you may not know, comes a subset of Rn. Then functions are defined as subset of Rn, you can talk about smoothness. Okay, Rn cross A cross B is also Rn A comma B is also a subset of some Rn plus 1. Okay, so this is a statement. There is a uniqueness part automatically coming. The uniqueness part is actually coming from here. You know why? Because look at X could be anything now. Look at single point X, A cross A to B. The interval A to B is connected. So that will be X here. Okay. So at one point G of A is fixed. The entire map is fixed is the statement of 2.1 here. Okay. For different values of G, for each fixed G, the corresponding maps are all fixed. These continuous things. If for each system you should same uniqueness, it will be follow for all of them. Okay. So the important thing is that why such a function exists. Automatically it will be unique. There is no problem from this part. It will be unique. Okay. So why such a function exists? Okay. So this is what we will be doing in the rest of the lecture today. All right. So proof of theorem 2.2. Any comments? Any lecture? Any questions? All right. Let us proceed. We shall first prove the statement for the simplest case when X is a singleton. When X is singleton cross AB is what? It is just AB itself. Okay. I mean homeomorphic to AB. A singleton point in the first coordinate, the second coordinate varies over an interval. So it is just an interval, right? So let us look at this property, this function. What is the meaning of this one? Let us state it separately. Take f from AB to S1. Actually, I have fixed the singleton cross AB. So singleton I don't have to write now. Take a function f from AB to S1, it's continuous map. T naught belong to R is such that E of T naught is equal to f of A. I have looked at f of A here, and I have picked up some point in R which will be mapped to that point FA by E. Okay, E of T naught is, remember, it is just E raised to 2 pi I T naught equal to FA. Okay, one single point you can write because it is a function of, it is a point of S1. Suppose you have done this much, then there exists a map G from AB to R such that E composite G equal to F. G of the starting point is T naught. So this is the statement when it's a statement of precisely this theorem when X is equal to a single point. Okay, so I have rewritten it in a different language with different notation. That's all. So let us prove this property. This property is called path lifting property. Why it is called path lifting property? A function from an interval to S1 is a path, right? We have been defining if it is a differentiable function and so on, it's a curve and so on. Here, there is no differentiability. I told you right in the beginning. Okay, if it is smooth, the lift will be smooth, etc. will be automatic here. So that is the second part. Okay, so just now what we are doing is pure topology. Okay, so that's a path, and this function G will be a lift of this one. When you push it down by E, that will be a function inside S1. Okay, so I am all the time having this picture in mind. So exponential function is from, R is standing above the real line and a circle is standing below, and this is the exponential function E. Okay, so let us do this for the singleton space. X is singleton, and for the entire interval I have to find a path. Okay, once again I use connectivity. Take A to be set of all points inside R. So G is defined on A to X as required. Actually, don't take anything X between A to B. You can take. Okay, it's an interval, right? The A to B could have been the whole of R also. That's why I have put R here. There is no restriction on this interval. It could have been open interval, closed interval, and so on. G be defined on A to X as required. As required means what? G of A is T naught. E composite G is equal to Fx, f of T, till you have reached up to X. So between A, T lies between A to X. That's all. Our aim is to show that this set A is the whole of AB. Okay. The uniqueness part already follows, but we have to show that it exists. How to show that it exists? If you show that this set A which I have defined is the whole of AB, then I am done. Then there will be function G from AB to R such that E composite that function is equal to our function F. Okay. So here again I am going to use that the interval AB is connected. Okay. So first of all, this little a is inside capital A. Why? Because one point I have already chosen. G of A equal to T naught, and single point function is continuous automatically. Okay, so this A is non-empty. We shall show that A is both open and closed. Then it will follow that it is the whole of AB. Okay, so open and closeness of this function is what you have to show of this set. So start with any point x naught inside A. What is the meaning of this? You have a function G1 up to x naught, A to x naught, with the property that G1 of A is T naught, E composite G1 is F on this interval. Okay, so there's a continuous function like this. On the interval, now G1 of x naught minus half to G1 of x naught plus half, the exponential function is a homeomorphism, where from here to S1 minus f of x naught, you throw away minus of f of x naught. So the f of x naught is there here because G1 of x naught goes to f of x naught. Keep that point, throw away its antipode, minus f x naught. That's also a point of circle. So you throw away that point. You get an arc. That arc is the image of this open interval under E. Okay, by a homeomorphism, 1-1 mapping. So there is a logarithmic function, which is the inverse, which I have denoted by ln of G1 of x naught. This suffix I don't keep on writing all the time because they are all log functions. This is just to indicate that the point fx naught is going to G1 of x naught here. Okay, note that ln of fx naught is G1 of x naught. This is what just I told you. So by continuity of f, we get a delta positive such that an interval around this x naught minus delta, x naught plus delta, okay, everything happening inside AB, f of that is going inside this V. Okay, what is V? V is open, sorry, V is U here. Okay, S1 minus this set. So we define G2 to be log of fx. So come back by the log function. So you go back to the R here. So fx is from AB, A to x naught to S1. From S1, you take logarithm function to define G2. Okay. Now what happens is, between x naught to x naught plus delta, I have one function. Up to x naught, I have another function. On the point, namely on x naught itself, both of them agree. Therefore, the two functions can be patched up to give a new function all the way from x naught to all the way from A to x naught plus delta. The function was defined only up to x naught by our choice here. Now I have extended it up to x naught plus delta. What does that mean? This x naught, an open neighborhood of x naught, is inside A. For every point, arbitrarily chosen point inside a small neighborhood, a small open interval is inside A. Therefore, A is open. Okay. The proof for A is closed is identical, but only you have to say this is not, and so on. So let us go through that one. Now suppose x1 is not a point of A. What does that mean? We don't have a function satisfying all these properties all the way from A to x1. That is the meaning of it's not inside A. Never mind. Take a u1 exactly similar way, namely s1 minus f of x1 thrown out. For this u1, okay, which is neighborhood of fx1, f is defined on the whole of A, whole of AB. By continuity of f, we get a delta 1 positive such that this interval around x1 minus delta 1, x1 plus delta 1, intersected with AB, okay, f of that is contained inside u1. So it is continuity of f. Okay. So now you take V as this interval, x1 minus delta 1, x1 plus delta 1 intersection AB. Okay. None of these points will be inside A. So V intersection A is empty. This is the point. Why? Suppose you have a point here belonging to A. That means what? Up to A, I have already a function. Again, the same way as I have done, I will define from that point to up to delta 1, I will define another function. Okay, another function G. So patching up these two, I will get a function all the way up to delta 1, which will include x1 also. And that's a contradiction. Okay. So this part is similar. Only thing is, you start with negation, then they get a contradiction here. Okay, so no point of V intersection A, no point of V is inside A. V intersection A is empty means V is contained in the complement of A. So complement of A is also open, which just means that A is closed. Okay. Once A is both open, closed, and non-empty, it must be the whole interval AB. If A is the whole interval AB, we have a function G defined on the whole interval AB as required. Okay. From the earlier part, the uniqueness follows. Okay. If you have original function f is smooth, then at each point in a small neighborhood, it looks like log of f, right? Log composite f. F is smooth, log of that one is smooth. So the function g will be also smooth. Okay, that is an additional thing, observation that you have to do. That's all. So the proof is over for the singleton space. Okay. Any questions? It is important to understand the part of this proof up till here before going further. So if you have any doubts, you can ask now. Okay, let's go to the general case. The general case, it follows that for each fixed x, the corresponding statement will become the statement for the special case, right? For each fixed x, we get a continuous function gx. Now, I will not just write it as g because it depends upon x. Gx from AB to R, such that gx of A is the given function gx. This is I am free to choose, and E of gx of t is h of xt for all t inside AB. So this is the conclusion of the first part, namely the case when x is singleton. So for each singleton, you have got a function on the whole of x cross AB. Therefore, you get a function g of xt equal to g of xt by this formula. Clearly, this is a function, and E of g of x comma t is h of xt. Okay, and g of xa is gx by very choice here. Okay, so by uniqueness of the part, it follows that this function is the function that we are seeking. The only thing is we have not proved that G is continuous. What we know is when you fix x, it is continuous. So from each interval to R, it is continuous. But as a joint function from x cross AB to R, why it should be continuous? The point of this thing is that the uniqueness says this is the function. So if the statement is true, the only thing that we have to do is to prove that this function is continuous. I have no choice now. Okay, it is not as if I have chosen something wrong. If the theorem is true, it has to be that this function is continuous. Okay, so that is the force enforcement by us because of the uniqueness part of the of the theorem that we have proved just now for the single case. Okay, so point-wise we have defined a function on the intervals. So on the whole of x cross AB, I have to show that it is continuous. Okay, so let us see how we prove this continuity. So what I will do, I will pick up a point x inside x, then I will produce an open neighborhood of that point ux inside x. I will restrict the function g to ux cross 0, 1. Okay, so I have cut down the space x to this neighborhood. On this neighborhood, I will show that it is continuous. You see, with each point it is continuous, that we know. But now suppose I can show that in a neighborhood of that point, cross 0, 1, it is continuous. Then automatically x will be continuous because this ux cross 0, 1, as x varies, this will be an open cover for x cross 0. Okay, an open cover restricted to each member of the open cover is function is continuous, the function is continuous. All right. So how to find this neighborhood on which the function is continuous? So this is the that is all that is remains now. Okay, we have to do this. Okay, so this is done in a very meticulous way here. Okay, fix some point x naught belonging to x. Okay, for each t belonging to AB, using continuity of h is continuous from x cross I to x cross 0, 1 to s1, right? At x naught point, comma t, you get a neighborhood vt of x naught in x and an interval jt around t inside AB such that h of vt cross jt goes inside this neighborhood, h of x naught t naught. Okay, I for each t I am going to, so I am not going to put it at t naught here. For each t you have to do. H of x naught t naught is a point. I have subtracted minus h of x naught. So this is an open subset which contains h of x naught t, x naught t, right? Therefore, there will be a neighborhood. Neighborhood of a point in the product space is nothing but product of neighborhoods. A neighborhood of Vt of x naught and Jt of t. Okay, that is the topology on the product space. So a neighborhood of the product point, namely x naught t in the product space, goes inside this open subset because H is continuous. Okay. Now fixing x naught, I am varying the point t on the interval. Okay. The interval is compact. But when I vary the point, the interval AB will be contained in the union of all these open intervals. These open intervals union, because each open interval contains t. So for every t you will find here. So therefore, AB is contained in the union of all the open intervals. So that is an open cover. Every compact space has a finite subcover. There is a Lebesgue number, blah, blah, blah. This is the standard analysis, right? So as soon as you have an open cover for the interval, you must have used it several times by now. You can partition the interval S0 less than S1 less than Sn and so on, such that each closed interval here, subinterval Si to Si plus 1, is contained in one of the members on the right hand side. So this is usual application of Lebesgue number, right? So several times even in Riemann integration theory and so on, you have done this one. Okay, Si plus 1 to Each of them is containing one of the intervals. So this is the way you subdivide the entire interval. Okay. So now for each interval, ti, some ti's, I don't know which they are. I equal to 1 to 3 up to n minus 1. I have n minus 1 of them. Correspondingly, I will have Vt1, Vt2, Vtn. They are all neighborhoods of the same point x0 in X. Take their intersection. Call that as V. V could be x0. That's the neighborhood of x0. It's intersection of all the Vti's, which depended on Ti's. But now I have only finitely many of them. You take the intersection. That is another neighborhood because intersection of two open subsets is open. So finitely many open subsets is open. So V is the neighborhood of x0 in X. And what happens to H of V cross Si plus 1? V cross Si plus 1 is contained inside Vti cross Jti. V always contains Vti because this is the intersection of all of them. Si plus 1 is contained Jti by our choice. Therefore, it's contained is this one. These are all of them contained S1 minus Hx0 Ti. Okay. I mean, T is a variable here. So I have to put corresponding Hx0 Ti. Right? So if H is contained inside here, remember E composite G is H. Therefore, G will be contained in E inverse of those things. The E inverse of these sets are nothing but R minus E inverse of this point. And these points are what? They are a set of discrete points. You choose one point above, then rest of them are n plus something. By adding an integer, that point, okay, you will get all other points. So this is E inverse of that. So you throw away all of them. What you have got is a disjoint union of open intervals. R minus that is a disjoint union of open intervals. Right? So G of V cross Si plus 1, they are contained inside these intervals. Okay, this is true for I equal to 1, 0 up to 1 n minus 1. Remember, this picture will change as I change from 0 to n minus 1. The points Ti's will be different, could be different. Okay, but for all of them, you have this picture. Okay, so for all I 0 to 1 n minus 1, pick up a yi inside R such that E of yi is this H of x0 Ti. You can always do this because E is a surjective function. Okay, all points of S1 can be represented by E of Vi. So do that. This yi, you choose whatever you want to choose. The rest of them are got by shifting, a yi n minus 2, yi n plus 2. Okay, so these are the intervals now. This entire thing will got by this picture because this is I have thrown away. Okay, the opposite, the antipodal point I have thrown away. So I have take only yi minus n by 2 open, yi plus n by 2 open. So all these intervals, disjoint union as n range from all over the intervals. This is the picture for R minus E inverse of this point. Okay, so right hand side is looks like this. G of this is contained inside this is a statement here. Okay. So so far we have done this much of topology. We shall now show that there is perhaps a smaller neighborhood U. Okay, this V may not work for x0 such that G restricted to G U cross AB is continuous. This is our aim. We wanted to show that for each point there is a neighborhood. Okay, if this V we have chosen to be intersection of all these, this may not work. It may be slightly larger, I don't know. Okay, so I am claiming that there is a smaller neighborhood which will work. So this is our aim, right? To show that G restricted to some neighborhood like this is continuous. So this we shall do it by induction. Okay, induction on what? 0, 1, 2, 3 up to n minus 1. There are n divisions of the interval, right? So this induction will be on this n. So here is the picturesque way of the proof. Okay, starting with S naught equal to A, S1, S2, blah, 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 Sn minus 1, Sn is P. So this is the way the interval has been divided. So this bottom thing is, you know, like a cylinder, it looks like. Bottom thing is our space X, and this is X cross I, X cross AB. Okay, so X naught is here. Why this share keeps coming in between? I don't know whether. Okay, I'm afraid of clicking that. The Zoom is all this. Okay, so what you have is this X naught here. Okay, you can think of this as V itself, doesn't matter. I have put it as X, no problem. Inside V, we are going to find out this U0, U1, U2, and so on, small, Un minus 1. Finally, on this Un minus 1, all the way down, the function will be continuous. So final picture will be Un minus 1 equal to U. That is going to be our neighborhood of this one. On that, we are going to show that the function is continuous. How do we do that? Start with the function here is continuous. We choose a neighborhood appropriately so that on S0 to S1, the function will be continuous. Then, knowing that the function restricted to S1 is continuous on this plate, choose a smaller neighborhood, something happens so that S1, this one is continuous. Now you can put together these two things together. What happens is, if you take U1 all the way from here to U1 to this one, U1 cross S0 to S2, the function will be continuous. Because you have drop out extra points of U0, so you have to restrict it to U1, because only from U1 cross this one, the second part is continuous. So that is the whole idea. So finally, you have to take the smallest one here for which it will be continuous. So let us see how the inductive step is worked out here. If I write down the inductive step for S equal to S0, N equal to 0, okay, the induction step will actually repeat. Okay, so carefully understand the first step itself, and then it is repeating there. Up to here, the same hypothesis you will take a smaller neighborhood U2 here, a smaller neighborhood U1 here, and so on. So that is what I have shown here. So listen to the proof of how the first step is working. Then you have to just repeat it. Okay, repeat it n minus 1 times. You have arrived at the proof. Okay, so let us see how. So what you have is G of V cross S1, S0, S1 is contained inside the disjoint union of Y0 minus n by 2, Y0 plus n by 2. These are the intervals. So this is the starting point we have, right? The whole of V is true. But what we want is at x0 comma A is S0, right? That is the function gx0 A. And that is given to be continuous. We start with, you see, G is continuous. So that is our starting induction hypothesis here. Gx0, okay? For each one, Gx0 equal to Y0. G is continuous. At x0, it is Y0. And belongs to this interval Y0 minus n by 2, Y0 plus n by 2. y naught minus 1 by 2, y naught plus n by 2. You can check. Okay, y naught is y naught minus 1 by 2, y naught plus n by 2. Okay, so here I have not written it correctly. I have shift y naught plus n minus 1 by 2 and so on. So this is not it is becoming increasing union here. It's not disjoint union. So notation is slightly different issue. So you have to take y naught minus n by 2 plus y naught plus n by 2, shift it by say add 1, then y naught plus 1 by 2 to y naught plus 3 by 2. So that is what it should look like. Okay, so there is an error here in notation. I will correct it. So you pick up that notation, pick up that interval, okay, to which x naught belongs. Then what happens? X naught, S naught cross S naught 1, is whole S naught 1 is connected, right? So G of that whole interval must be inside this interval. The whole of them is contained inside disjoint union. So it can't jump into another disjoint set by the connectivity of this one. Okay. So using connectivity of G, we get open set, okay, continuity of G. We get, so first of all, an open set U naught contained inside V around X naught. So the G of U naught is inside U I naught. So use the continuity of G to get a smaller neighborhood around X naught contained inside V, which satisfies one. Then Gx is continuous. When you restrict it to a single point, G of X cross S1, S0 to S1, which is the Gx of this one, this is a connected set. Therefore, this entire thing will be contained inside this I naught. So this is true for all X naught, all X inside U naught, because U naught has been chosen such that G of U naught is inside the same interval. So that is why I cannot take the whole of V, but I have to take a smaller neighborhood. This can be ensured by the continuity of G itself to begin with. Okay, so therefore we have G of U naught cross S1, S0, S1 is contained in I naught. One single interval, you have the exponential function, which is the injective mapping, right? Therefore, you have the logarithm function, which is the inverse of that. Therefore, you can write G as nothing but ln of H. G of ln of H is the same thing as saying E of G is E of ln, which is H. That is given. Therefore, by applying the inverse function here, G will be equal to ln of H. Now, once you have this formula, continuity of G follows. Why? Because ln is continuous and H is continuous. In fact, if H is a differentiable function, then G will be also differentiable. So this proves the continuity of G on U naught cross S naught S1. So that is the starting point of the induction. Okay. The starting hypothesis was that on the bottom space here, the given function G is continuous. So now we have got up till here it's continuous. Now what is the hypothesis? This becomes the bottom for the next cylinder. On that one, function is already continuous. So repeat it. So you may have to take a smaller neighborhood on which the whole thing goes into one single interval. Okay. Once that goes into one single interval, this entire block, okay, U1 cross S1 to S2, that will go into same interval. Therefore, it will be log of, the function will be log of something. G will be equal to log of H, ln of H. Therefore, it is continuous up till here. Repeat this argument. Each time you may have to reduce the size of the interval, size of the open subset around the point x naught. The neighborhood may have to be chosen correctly, because the interval on the right hand side keeps changing. See, that is the beauty. Okay, the TIs are different. From here it is from T naught, here you have some other T1, here T2 and so on. Okay, within that you will get one single interval each time, and therefore one single logarithmic function, and therefore the restricted functions are all continuous. They patch up already because there is one single function already. Function, there is no problem. We have, by the first part, we have already got the function. The continuity was a problem. So for continuity, what we have done is, we have first chosen a single point in x naught, in x, and produce a neighborhood of that point, such that on that neighborhood cross AB, it is continuous. Okay, so that is the inductive hypothesis, inductive step here, which is just repetition of whatever happens to the first one. Okay, I have written it completely, but as I see that these things have to be changed. Okay, so there is some typos here. The case of the singleton set itself is one of the theorems that we wanted to prove in the first part of these lectures, maybe second week or third week. We did what? We introduced the turning angle theorem or whatever in defining the signed curvature of a plane curve, right? At that time, I told you that I will give you the rigorous proof later. All right, so now I have given you the rigorous proof of that one also. I will just reproduce that one. I'm not going to prove it again because we have just proved that one. It was proposition 1.8. It was called path lifting theorem. It just said that if you have a function, continuous function from an interval, okay, inside R to S1, okay, J could be finite, infinite, whatever. T naught belonging to J, phi naught is R, such that phi of T naught is one single point I have defined as cos phi naught, sin phi naught. Then you have a whole lot of them, the entire thing continuously on the entire interval, phi from J to R, such that psi t is cos phi t plus sin phi t. You can write like this, but why this phi t should be continuous? You will have to look at cos inverse or sin inverse. What is this? Cos inverse, sin inverse are not defined on the whole of the circle. They are defined only partially on, just like log functions, right? So this is all this ambiguity will be removed by this one, and this is precisely the statement here. Instead of cos phi t sin phi t, what I have got here, e power 2 pi I phi t. Okay, so this theorem gets proved. All right. I would stop here. I would like to make a small comment about yesterday's last part, which I deliberately postponed today. Namely, this Kodaji minority equations, which is purely computational and totally elementary computations. Okay. No point if I am doing this. I have nothing to explain there. You have to do that yourself. Okay. So what I want to explain, I will explain. I will take 2 minutes more here. Anyway, I did not take those extra minutes, doesn't matter. So these are called Gauss equations. What are they? I will tell you. Start with a sigma, which is a surface patch. Gauss equations are about the second derivatives of sigma. Sigma uu, sigma uv, sigma vv. Remember, they are vectors inside R3. We have sigma u, sigma v, independent vectors in the plane, tangent plane, and this n is the normal vector. So sigma u, sigma v, n, they form a basis for R3 as a vector space at each point. Therefore, every vector can be written as a linear combination of these three vectors uniquely. So write them. Let's call the coefficients here as gamma 1, 1, 1, gamma 2, 1, 1, and so on. Okay, depending upon sigma uu is 1, 1, 2. 2 correspond to sigma v. The last thing has to be L by the very definition of L. What is L? Remember, it is sigma uu dot n. You dot this one with n, what you get is L here, and n dot sigma v, n dot sigma u are 0. Therefore, you have these equations. You don't know what gamma 1, gamma 2, gamma, etc. These gamma ijk's are called Christoffel symbols. Okay. So I don't know what symbols Gauss used. These are called Gauss equations because Gauss had done them. But thinking of them writing like this neatly must be due to Christoffel. So they are called Christoffel symbols. They have lots of symmetrical properties and so on. Okay. None of them I am going to use in this course. All right. So these are details which have to be studied by people who want to study Riemannian geometry finally. Okay, what I am going to emphasize here is what are these gamma ij's for the surface? Sigma, surface patch. And that is called Gauss equation. Gamma ijk's are given by this. There are 6 of them. You have to determine this. This looks horrendous here. It is not so difficult as the formula looks like, if you understand what is going on. Okay. How do you do that? You just take, you see, remember, the sigma u and sigma v are non-zero independent vectors, but they are not orthogonal. Not necessarily. Therefore, when you take dot product with sigma v, it is not easy equation. Dot product with n will just give you L. Dot product with sigma v, of course, this Lm and etc. will disappear. Only these two will remember because sigma v dot sigma u is not 0. So what is it? It is F. So there are EFGs coming here. Okay. So for 3 equations, dotting with sigma u, sigma v, you get 6 equations. 6 equations, 6 unknowns, elementary linear algebra. Solve them, please. Over. Okay, that is Gauss equation. Exactly similarly, minority equations are what? By differentiating the Gauss equation with respect to u and v and taking the difference of Lu, Mv, lot of terms cancel out fantastically. Okay, I will tell you why they cancel out also. After that, you have very neat equations like this. Okay, so what you do here, already you have sigma uu, sigma uv, sigma vv. When you have differentiate once more, you get, third order differential equations. But because of the smoothness condition we are assuming, what you have is you can permute them. Sigma uuv is sigma UVU. Similarly, sigma UVV is sigma VVU. Use this to simplify and cancel out a number of terms. This is all that is there. Rest of them is not very easy, but unless you do them, it won't be of any use to you. Okay. So that's it for today. Thank you. If you have any questions, you can ask. Otherwise, you can disperse and come for the tutorial class.